Welcome! Today we learn how to integrate using substitution. It's all based on the magic of the chain rule. And I write you down a formula which helps. So if you have a function g and a function u, and we combine them in this way, then we can write down the antiderivative directly. This is just g of u of x plus constant. So that's the magic formula. And why is this true? And that's where the chain rule comes in. So differentiate, we take the derivative of g of u of x, and by the chain rule we differentiate g, so we get g prime u of x, and then we have the inner derivative times u prime of x. So we verified that if you take the derivative of that, the constant goes to 0. That gives us this inner part. So let's look at an example. So example 1, I'm integrating cosine x squared 2x dx. If you look at this integral, we can immediately see that's the derivative of this inner function. So we can immediately write down that's just sine of x squared plus a constant. We take another example. If we integrate the square root of 1 plus x, also here we can see this is a combination of two functions, but the derivative of the inner function is just 1. So this is actually just then 1 plus x to the 3/2. We have to adjust the constant divided by 3/2 multiplied by 2/3 and plus c. Double check, is this right? When we differentiate this, we get the 3/2, cancelling that. 1 plus x to the 1/2, which is this, and the constant goes away. We want a process which formalizes this nicely. Let me just write down the example again, which we had. So we had the integral of cosine x squared and times 2x. So what we do is we identify part of this formula which we want to call u. Let me just take this x squared, call this u. Now what we do is I always kind of make below the equal sign, I make a little box where I say, okay, this is u, this is x squared, and then du is equal to 2x dx. And sometimes it's helpful also to solve for dx, right? dx is equal to the du over 2u. So I always put it in a little cloud. And so what we have here is we just substitute now in everything. So what we do is we write it down in terms of u. So what we get is cosine of u. And we still have the 2x here, and the dx I replace with du over 2x. Sorry. So this I replace with du over 2x. That has cancelled nicely. This gives cosine u du. Now we have an integral which we know. This is a sinus u plus c. And finally we back substitute, we replace u again with x squared. So this is a sinus of x squared plus c. So let me just write down what we do, and then afterwards we will look at a lot of examples. So what we do first is identify part of the formula. Call it u. Then we compute the du. Maybe solve for dx. Now replace everything by u. So substitute. And the last thing is integrate and back substitute. So let's practice this in a few examples. I wrote you down the examples already here. Let's just go through them. So this is a little bit of drill. So the first example is we integrate log x. So 1 over x dx. So the first problem is to find what we actually substitute, what we call u. And sometimes you have to try, you don't want to substitute x itself, but log of x is a good choice here. We call this u. So let's just see, we have a u is equal to log of x, natural log, then du is equal to dx over x, and we maybe solve also for dx is equal to x du. Let's just see what we get. Taking this as my substitution. So what we get is now the integral u 1 over x, the dx becomes x times du. That cancels away, and we have just the integral u du, which is u squared half plus c. And the final thing we do is we back substitute the log x. So this is log of x squared over 2. That was example 1. Example 2b is e to the x squared, e to the x cubed times x squared. So in this case also you smell what the u should be, right? You want to also see the derivative appearing. So it's kind of really smells that this is equal to, we shall take this equal to u. So we take u is equal to x cubed, du is equal to 3x square dx, and then again dx is equal to du over 3x squared. So that's our substitution. Let's just see what we get. We get e to the u, x squared we leave, and we have the dx is du over 3x squared. That goes away, and we have integral e to the u du, which is very nice because we know how to integrate e to the u. That's e to the u plus c. And finally we back substitute e to the x cubed. That's our answer. This is example b. A good choice usually is, if you have a square root something, to take everything which is under the square root, to take this as u. So let's take u is equal to 1 plus x squared, not just take x squared plus 1 plus x squared, and the du is the 2x dx, and the dx is equal to du over 2x. So that's our substitution, and let's plug it in. So what we get is x, and then we have just the square root of u. We just hope that the x will go away, and indeed it goes away because we have dx is du over 2x. So the x cancels, and we have the integral 1 over square root of u du, which we know how to integrate because this is u to the minus 1 half. So this is, actually I forgot the factor 2 here, and when we integrate 1 over square root of u, we get 2 times the square root of u. So we get 2 times the square root of u times 2 plus c divided by 2, which is square root of u plus c. And finally, the last step is we back substitute the 1 plus x square. So this is the square root of 1 plus x square plus constant. Example D. Example D is 2x over 1 plus x to the 4. That's already a little bit more challenging because it's not so clear what we should take here. We want this to be the derivative, so that's a hint that we should take x squared and not x to the 4th. If you take x to the 4th or 1 plus x to the 4th, we don't end up with that cancellation. So that's you will get a feel for it, but we take u is equal to x squared, and then du is equal to 2x dx, and dx is equal to du over 2x. You see that 2x appears here. That's good news. And let's just plug that all in here. So we got 2x, and then we got 1 plus u squared, and then the dx has been replaced with du over 2x. The 2x cancels away, which is very nice. Then we have the integral 1 over 1 plus u squared du. You are now familiar with this, right? Because this appears in, this is the Cauchy distribution with the 1 over pi here, Cauchy distribution in statistics. And so we know this is the arctan. The final step is to back substitute in u is equal to x squared. So we get the arc tan x squared plus c. That was example D. Also here, maybe a little bit more challenging because we have trig functions. We could actually have written it as sinus x over cosine cubed x, which would have been even more challenging, because here we kind of might be reminded that if we take the derivative of the tangent x, we get 1 over cosine square x. So that's always a good thing. Look for derivatives of part of the function. And in this case, when we take u is equal to tangent x, then du is 1 over cosine square x dx, and dx is equal to cosine square x du. So that's what we substitute in here. So we get the integral of u over cosine square x, and then we have the dx becomes the cosine square x du. Nicely cancels out du. We know how to integrate this, and we back substitute. That's the last thing. Back substitute the tangents in, so we get tangent square x over 2 plus constant. By the way, this is an example which you have already seen as a challenge, where you have to guess. When we have not this technique, you have to kind of guess the answer. And finally, the last example is an example which you have also seen in statistics. It was the mean, essentially the mean of the Cauchy distribution. So when we computed that, so that's f, when we have x over 1 plus x squared dx. So in this case, again, it's not so clear first what you want to take, but x squared is definitely a good choice for you because you have essentially the derivative here. So let's try that. But if you have a constant plus, so it's actually good to take here 1 plus x squared, and then du is equal to 2x dx, and dx is equal to 1 over 2x du. So that's our substitution cloud here, and we plug that in here. What we get is the integral, so 1 over u, x over u, and then the dx is 1 over 2x du. This cancels away, so we have the integral of 1 over 2u du, and we know how to integrate that, right? 1 over u, we have 1 over u, that's the log, so the natural log of u over 2 plus c. And the final thing is we have to back substitute that in. So the u has been the 1 plus x squared, so it's the log of 1 plus x squared plus c the whole thing over 2. So these are the examples. Okay, let's look at a few more challenging examples. The first one is integrating, similar to what we have seen, log x to the 5 over 5x dx. But we smell that log x is a good choice, right? U is equal to log x, and du is equal to 1 over x dx. So dx is equal to du times x, and we plug that all in. We get the integral of u to the 5 over, and then we have 5x, and then the dx becomes the x du. So that cancels again. So this is integral u to the 5 fifths du, which is u to the 6 over 30 plus c, and we plug that in again. We plug in the back substitute the log of x. This is log of x to the 6 over 30. Second example, integral of 1 over x times log x. So again, we have made good experiences by changing, by substituting log of x. Let's do that again. U is equal to log of x. So du is equal to 1 over x dx. Now we don't actually get a nice cancellation like before, right? But we have just x times du. No, it works. We actually get the cancellation also. So we have 1 over. So we have 1 over u. We leave the x here, and we substitute the dx, which is x times du. So we get again the cancellation, and so we have the integral 1 over u du, which is the log of u. And we back substitute in the u. This is the log of x plus c. Now that's more challenging, because it's not so clear what we should take. Shall we take the tangent x as u? That doesn't work, but we can write it as sinus x over cosine x. And then we might just realize the sinus x is the derivative of the cosine x, so that cosine x is a good choice as a substitution. So let's do that, and in this case we get the integral of 1 over u sinus x. I leave the sinus x here, and then the dx becomes the minus du over sinus x. Fortunately that cancels away, and we get the integral du over u, and we know what that is. That's minus the log of u plus constant, and we can back substitute in. It's the minus the log of the cosine x. So we are almost there. The last example is a tough example. So we have to maybe guess our substitution. In this case, u is equal to x squared plus 1 works. So du is equal to 2x dx. And dx is equal to du over 2x. Maybe you also solve for x, right? So we have x is equal to the square root of u minus 1. So let's just see what we get if we substitute that in. So x to the 3 we actually have to plug that in here because there's no cancellation. That's why it's tough. So we get the square root of u minus 1 cubed. Here we get the square root of u. And for the dx we get the 2x du over 2x, which is du, and then the 2x is again the square root, 2 times the square root of u minus 1. So now there is some cancellation going on. Let's just write this. So this is square root of u minus 1 cubed over square root u minus 1 is just square root of u minus 1 squared, which is u minus 1. And then we have 2 times the square root of u. So we have this, and this doesn't look good yet, but we can take it apart, right? So this is the integral u over 2 times square root of u minus 1 over 2 times the square root of u du, which is just square root of u half minus 1 over 2 times square root of u. And we know how to integrate the square root, right? So that's u to the 3 half times 2/3. And we also know how to integrate 1 over 2 times square root u. That's just the square root of u minus the square root of u. And we back substitute in, so the u was x squared plus 1, so this is x squared plus 1 to the 3 half. The 2 cancels over 3 minus, and the square root of u is the square root of x squared plus 1. You should put the c here, so plus c. That's it for today.